We have a thin convex lens, and the radius of curvature of both the surfaces are 25 centimeters. And let's say the material is made up of a medium which has a refractive index of 1.5. We need to figure out the focal length of this lens when it is kept in two cases, air, in the second case in the oil of refractive index 2.0. All right, let's do this. So we've been given the radii of curvature and the refractive index of the material, and we need to calculate the focal length. So what expression connects the focal length and these things? The only thing that comes to my mind is the lens maker's formula. That's what connects the focal length and the properties of a lens, right? So remember what lens maker's formula is? We derived this in a previous video. 1 over f, where f is the focal length, equals n2. n2 is the refractive index of the material of the lens divided by n1, which is the refractive index of the surrounding medium, minus 1 times 1 over r1 minus 1 over r2, where r1 and r2 are the radii of curvatures of the two surfaces. So let's apply this formula and see what the focal length is. So let's do this. So let's look at case 1. So 1 over the focal length, let's call that focal length as f1 for the first case, whatever focal length we get. That equals n2 over n1. Well, n2 is the refractive index of this medium. So that's going to be 1.5 divided by n1, which is the refractive index of the surrounding medium, which is air. So for us, refractive index of the air is 1, pretty much 1, minus 1 times 1 over r1 minus 1 over r2. Now r1 and r2 are the radii of curvature of the two surfaces, and both are 25 centimeters. So is it, let's see, is it just 1 over 25 minus 1 over 25? We have to be careful. Remember, whenever you're using formulae or when you're substituting into a formula, please use sign conventions. So sign conventions are extremely important. The signs that we use over here are Cartesian sign conventions. And the convention goes like this. We are always, let's first draw a principal axis. We are always going to choose the incident direction. Let's call this as the optic center. Okay, we're always going to choose the incident direction as positive. But the big question is, which is the incident direction over here? Well, you know what? You can choose whichever direction you want to be incident over here. So let's just assume the right side to be incident. So let's say this is our incident direction. Then all the positions to the right of the optic center is going to be positive. We're going to treat this as the origin. And all the positions to the left of the optic center will be negative positions. Negative positions. And because the incident direction is to the right, so you can imagine there's an object somewhere over here, the rays of light are going to hit this surface first. And so we'll call that as our surface 1. And then the ray of light will hit this surface. So that will be surface number 2. So you could have chosen the left side as also positive. That's also, I mean, you could have chosen the left side as incident. Then this would be surface number 1. And this would be surface number 2. So you're free to choose whichever direction you want as incident, but accordingly, your surface 1 and surface 2 will change. So now that we have this, let's see which radii are going to be positive and which radii are going to be negative. So remember, these are spherical lenses, so they are parts of a sphere. So if you just draw this imaginary spherical surfaces that they are part of, can you see that the first surface, it will be a sphere like this, which has the center on this side. Since the center is on the positive side, the radius of curvature of the first surface is going to be positive. So R1 is going to be positive 25. That's correct. Minus R2, 1 over R2. Now notice, when you consider the second surface, its center of curvature, its center is over here, which is on the negative side. As a result, its radius is going to be negative 25 centimeters. Therefore, it's going to be minus 1 over negative 25. So let's put that over here, negative 25. That's the only thing we need to be careful about over here. And so now we can go ahead and solve this. 1.5 divided by 1 is just 1.5. Minus 1 is 0.5 times 1 over 25 plus 1 over 25. The negative becomes positive. So you get 2 over 25. And 0.5 times 2 is just 1. So that gives us 1 over 25 again. This is 1 over f1. And therefore, the focal length in the first case turns out to be 25 centimeters. And there we have it. That is the focal length in the first case. Also notice that the focal length we're getting is a positive value. What does that mean? Well, since the focal length is positive, it means the principal focus lies on the right side because that's where the positive side is. So our principal focus, let's write that down, is going to be somewhere over here at a distance of 25 centimeters from here, which in turn means that if we have incident beam, which is like this, incident rays of light is like this, then these rays will get converged at this point. And that's what we would expect, right? If it's a convex lens, we would expect it to converge at some distance. And there we have it. All right, now let's go to case 2. In the second case, our lens is kept in an oil of refractive index 2.0, which means the surrounding medium of our lens now is going to be oil with the refractive index of 2.0. So it would be a great idea to pause the video over here and see if you can try this yourself. All right, let's see. Well, if you think about it, notice we're still going to use the same formula, the lens maker's formula. What's going to change? Well, N2 is going to remain the same. The material has not changed. N1 is now 2.0 because the outside medium is now this oil. The radius of curvature is going to remain exactly the same. Whether you put it in oil or whether you put it in air, the radius of curvature is not going to change. And so if you use the same sign conventions, everything will remain the same. So the only thing that's changing is this number. This number is going to become 2.0. So again, if you've not tried this before, great idea to again pause the video and see if you can try this now and do the algebra. So our new focal length, let's call it as f2. Now this will be 2.0. So this is going to become 2, and everything else will remain the same, which means this remains the same. Let's see what happens over here. This is going to change now, isn't it? So what's going to happen over here? Well, 1.5 over 2 minus 1. We can take the common denominator. That's going to be 1.5 minus 2 divided by 2. Let's get rid of this. Okay, so what we get now is 1 over f2 equals 1.5 minus 2 is minus 0.5. This 2 cancels. So divide by 25. And 0.5 is half. So it's going to be minus half over 25. That's going to be minus 1 over 50, which means if you take more space over here, which means f2, let me write that down somewhere over here. So let's say f2 is minus 50 centimeters. And there we have it. That's our result. But here's the question. What does it mean that our focal length is now negative? Again, great idea to pause the video and think about this if you haven't already. All right, so negative just means one thing. The principal focus has to be on the negative side. That means the principal focus is over here, and this distance now is 50 centimeters. But what does that mean? Well, what that means is if you have incident rays, let's draw incident rays with purple now, let's say. If you have incident rays like this, then after refraction, will the rays of light get focused here? Well, that can't happen. We know that. But what can happen is that the rays of light will diverge away, and they appear to diverge from this point. That is what this means. That's the only thing that this can mean. In other words, this negative focal length is telling us that our lens is now a diverging lens. And this might sound weird to us because it's a convex lens. How can convex lens act as a diverging lens? Well, it turns out, as we can see from the formula, as you can see from this, it turns out that it can behave like a diverging lens when you put it inside a different medium. And in fact, if you look carefully, the reason it's acting like diverging is because the medium outside has now become denser than the medium which is inside. And as a result, our rays of light are going from denser to rarer medium. And so they're going to refract in the opposite direction. They're going to refract away from the normal. And if you actually draw the normals, you'll see that this is happening. Great exercise to try and convince this to yourself by just drawing ray diagrams properly. But this is what's happening. So from this example, we can learn one very important thing, that even if you have a converging lens in the air, that same lens can become diverging if you put it inside some medium which has a higher refractive index than the material of this lens. And so this is how we can use lens maker's formula in different cases to figure out what the focal length is.